Okay. In the next few lectures, we will discuss some graph theory. So a simple graph, or for most of the purposes, we call it a graph, is a pair. Say G is equal to V comma E, where V is a set of objects that we call vertices, and E is a set of two element subsets of the vertex set, and the elements of E are called edges. So basically, you can think of E as a binary relation between the pair of objects. Now, let us look at some examples. So here are three examples. So let us say that V is the set A, B, C, D, and E is the set of two element subsets AC, AD, and BD. Okay, so this defines a graph. Similarly, you have this infinite set Z as your vertices, and two numbers A and B. A comma B belongs to the edge set if and only if their difference is 1. Similarly, let us look at V as the set of numbers from 1 to 5, and two numbers I, J belongs to E if and only if their difference is equal to 2. Okay. Now, these are all examples of graphs. Now, when the vertex set is not finite, then we say the graph is infinite, and otherwise it is a finite graph. The cardinality of the vertex set is called the order of the graph, and it is usually denoted within two parallel lines. And the size of the graph is written as as we write norm of something. So this is the size of G, which is the number of edges. So the order of graph is the number of vertices, and size of graph is the number of edges. Now, one of the main reasons people use graph is that it enables us to visualize the several properties of the relations that we are considering, and this can be visualized in many senses, many cases. So for this, what we do is that we map the vertices to distinct points on the plane, and then whenever a pair is in the edge relation, we connect them using a simple curve or a line segment on the plane, right? So then what we see is precisely an alternate representation of the same graph that we are looking at. So here is an example of how we usually represent graphs on R2. So here you have these points A, B, C, D, E, F, right, which are the vertices of a graph which are mapped to points on the plane. Now, since AB is an edge, right, in the graph I'll draw a line segment connecting A and B, and similarly for BC, AD, BF, C, E, and FE, right? So all these edges are drawn as line segments here. And so we can see that this graph is precisely the graph which is drawn here, right? So this is easy to visualize, and you can now also try to see like what kind of other things that you can think of the relations, right, from this picture. So precisely what are these we are looking at is something we will come to see when we look at more definitions. But one can see the difference between the set description and the pictorial representation, right? There is something much more visible here. Okay, now suppose you are given a graph G with vertex set V and edge set E. And let us pick a vertex, let's say V in the graph. And let us say small e is an edge of the graph. We say that the vertex V is incident with the edge E if V is an element of E, right? Because E is a pair of vertices. So one of them is V, then we say V is incident with E. Now, for an edge E equal to, let's say, set U comma V, U and V are called endpoints of the edge E. Okay? So again, the notion why is it called endpoints comes from the pictorial representation, right? So these are basically the endpoints of the line segment that we use or the curve that we use to represent the edge. Now, we say that U and V are adjacent if UV forms an edge, or you say that they are neighbors of each other. So U is a neighbor of V, V is a neighbor of U. Then we sometimes write the edge, in a compact form. Let's say UV without any space between them. And then we say that this is representing the edge. It's basically the subset of two-element subset of V, U comma V, but we write it as UV to make writing easier. So this is some notion that we will use. This notation will be followed whenever possible. Sometimes it makes sense to use the other notation, but otherwise we will stick to this. Now, given two edges which are distinct, they are said to be adjacent if they have non-empty intersection. Okay, so if E and F are distinct edges, and then E intersection F is non-empty, then they are said to be adjacent. Now, a graph in which every pair of vertices are adjacent is called a complete graph. Okay, this is something which we will use many times. So, complete graphs are graphs where every pair of vertices are adjacent. Suppose we are looking at a graph whose order is n, then we denote by kn the complete graph on these n vertices. Okay, so if you have exactly n vertices and the complete graph, then it is represented k subscript n. Here are some examples of complete graphs. So the first one is a complete graph on just one vertex. There are no edges, and then you have a complete graph on three vertices, which we call K3, right? So any two of them are adjacent to each other. Similarly, any two of them are adjacent in K4, and then you have K2 on two vertex complete graph. Now, suppose you are given a graph, and you are given a subset of the vertex set, let's say S. So S is a subset of the vertex set. We say that S is an independent set in the graph G if for any two elements of S, let's say S1 and S2 are any two vertices in S, S1, S2 is not an edge, which means that among this subset of vertices, there is no edge between them. Okay? These vertices can have edges to outside the set S, but they cannot have any edges within this set. So then we say this is an independent set. Now, a graph, H is said to be. So let us look at an example, maybe. So here is a graph, and then we look at some independent sets. So let me say that I am going to add this vertex to my independent set. Then I cannot add 4 or 2 because one has edges to 4 and 2, right? So but I can add 3 because there is no edge between 1 and 3, right? So 1, 3 is definitely an independent set, right? 1 itself is an independent set. 1, 3 is an independent set. Now, can I add anything more? Well, I cannot add 2 or 5 because 3 is adjacent to both. But 6 is not adjacent to either of 1 or 3, so therefore I can pick 3 also. So now I get another independent set, 1, 3 and 6. This is an independent set in the graph because between themselves there is no edge between them, right? Similarly, if I wanted something else, maybe I will say that okay, I don't want this, but I will pick let's say this, right? So now if I pick 5, then I cannot choose 3 or 6, but I can choose maybe 2 or 4 or 1. One of these I can pick, right? So let me pick 2 itself, maybe, right? But then I cannot pick anything else, so therefore, these two forms an independent set. So this way we can look at several independent set possible. There are several questions one can ask, like what is the largest independent set? What is the then and then what can you say about the number of uh, independent set with other parameters and things like that? We will come into that later. Now, given a graph H, let's say V dash A dash, we say H is a subgraph of the graph G if V dash is a subset of V and E dash is a subset of E. Okay? So a graph H is a subgraph of G if V dash is a subset of V and E dash is a subset of E. Now let us look at some examples. So given the graph, let's say G is equal to VE and H is equal to V dash E dash. Okay? Now where V is the set 1, 2, 3, 4 and E is the set 1, 3, 2, 4 and 3, 4. V dash is a set 1, 3, 4 which is a subset of V and E dash is a subset of E, right? 1, 3 and 3, 4. And we see that H is a graph on this vertices 1, 3, 4 with the edges 1, 3 and 3, 4. So therefore H is a subgraph of G. We usually write it using the subset symbol. Okay, so H is a subgraph. Subgraph. Right? H is a subgraph. Now let us look at another example. Let us G is equal to V comma E and V is the set A B C D E F. Okay. Now E is the set A B A C A E D E C E and E F. Right. Now given this graph, and I look at the other vertex at V dash A C E F and E dash is A B D and E F, right? So V dash is a subset of V, right? A B C D E F, and E dash is a subset of E, right? All these edges are present here also. But now one can ask whether H is a subgraph of the graph G. It is not, because H is not a graph. Okay. Why is H not a graph? Because H has the vertex at A, C, E, F, and H set A, B, D, E, and E, F. But D, E cannot be an edge in H because D is not a vertex of H. So therefore, even though V dash and E dash are subset of G, H is not a subgraph. So that is why our definition clearly says that a graph H V dash E dash is a subgraph if this. So first of all, H must be a graph. Which means that it is defined properly, that the edge set is a 2-element subset of the vertex set. If that is not the case, it is not a graph. Okay, now a subgraph is said to be an induced subgraph if for every pair of vertices in H, the edge xy is in H whenever xy is an edge of G. Okay, so for any elements in the graph, any vertices in the graph H, the edges that are present between themselves must be present in H also, right? So whenever it is that edge is there in G, it should be there in H. It is only for the edges within the vertex set of H. So it's so if V dash is subset of V, we can write G square bracket V dash to say that we are looking at the subgraph induced by the vertex at V dash. Because now once we know what is the vertex set, we know what are the edges, because all the edges between them selves must be there, right? From the graph G, whatever is there, that must be here also. So we write it this way. And here is an example. So given the graph G as below, right? And look at the subset 1, 2, 4, and 6. Then you can see that the induced subgraph is represented as this graph, right? So 1 is there because 1 is a vertex here. But 1 to 2, 4, and 6, there are no edges. So therefore, there is no edge from 1 to any of these vertices. 2 to 4, there is an edge, and that is present here. 4 to 6, there is an edge that is present here. 2 to 6, there is no edge that is not here, right? So therefore, this is a subgraph which is an induced subgraph. Here are a couple of more examples. So you have a graph G with two subgraphs H and H dash. So H and H dash are both subgraphs of G, one can easily see. Now H is an induced subgraph because if you take the vertices in the outer four vertices, that vertices, all the edges between themselves are present in H. Now if you take H dash, on the other hand, H dash has all these four vertices present, but it also has the middle vertex. But now the middle vertex, there is only one edge going to the vertex here. On the other hand, since we have all the vertices of G, all the edges also must be present, but that is missing. So therefore, it is just a subgraph. It is not an induced subgraph. Now, given two graphs G and H, okay, we say G is isomorphic to H, and we write using this isomorphism symbol. If there exists a bijection which takes the elements of V to elements of V dash, right? So V to V dash, there is a bijection, which is also edge preserving in the sense that if UV is an edge, then phi of U, phi of V is an edge, and whenever phi of U, phi of V is an edge, UV must be an edge. The inverse map also should preserve the edges, right? So which means that UV is an edge in the graph G if and only if the images phi of U, phi of V is an edge in the graph H. Such a map phi is called an isomorphism. Okay, so if you have an isomorphism between two graphs, they are said to be isomorphic. So the graph properties that are that doesn't change under isomorphism or preserved under isomorphism are called graph invariants. So we will use some of the invariants in the future. Now here is an example of isomorphic graphs. So even though they are represented differently in the plane, one can verify that they are exactly the same graph, right? So or isomorphic. So you have 1, 2, 3, 4. This is a complete graph on four vertices. And here I have another representation of a complete graph on four vertices with edge vertex levels as different, right? So A, B, C, D. If I can map, 1 to A, 2 to C, 3 to D, and 4 to B, you get an isomorphism because all the edges are preserved. In fact, any injection is an isomorphism because it is automatically a bijection which preserves the edges because they are complete graphs. But not true in all cases except for complete graphs. Okay, now the graph G bar obtained by making every so you take the graph G, then you make all the non-edges, which means that any pair of vertices which is not forming an edge is an edge of the graph G bar, and every edge of the graph G I will make a non-edge. So I just remove those edges, right? So such a graph is called the complement of the graph G, right? So given this 5 vertices, right? You have this this graph. Now what is the complement? The complement is, so whatever edge is not present here, for example 1 to 4 there is no edge, right? Similarly 1 to 3 there is no edge, 2 to 5 there is no edge, 2 to 4 there is no edge, 3 to 5 there is no edge, right? So these missing edges of the graph G are going to be present in G bar, and all the edges that are present in G must be missing from, right, G bar. So therefore you get G bar as the complement of the graph G. Okay. Now, in this particular case, it happens that the graphs happen to be isomorphic. Okay, so G is isomorphic to G bar. One can easily verify that this graph is also exactly like this graph. So you can look for an isomorphism. Now, the number of edges, okay, this is an important parameter that we are going to study. Number of edges incident with a vertex is called the degree of the vertex, usually denoted by d of v, unless we need to use a different notation when we will mention it. Okay, so d of v is the degree of v. And in this graph, for example, you can see that the degree of the vertex x is 5 because it has all these 5 edges incident with it. Right, this edge, this edge, this and this, right? So all these 5 edges are there. So therefore the degree is 5. Similarly, the vertex y has degree 3. It has 3 edges incident with it. And the vertex z has degree 1 because it has only one edge incident with it. You can see that other vertices also has degree 1. Now, if I am given a graph, I look at all the vertices and look at the degrees and find the minimum value, right, among all the vertices. So that is called the minimum degree of the graph. It's denoted by delta, which is also an important parameter. Similarly, you can look at the maximum degree, which is denoted by capital delta. So capital delta is the maximum or all the degrees. Now, the maximum degree of this graph is 5 and minimum degree is 1. One can easily verify. A graph G is said to be regular if all the vertices have the same degree. Okay. Now, this graph was not regular because we had several degrees. But on the other hand, these two graphs are regular, right? Because every vertex has a degree 2 here and also here. Similarly, this graph, every vertex has degree 3. So they are regular graphs. Now, the first theorem in graph theory is usually this, that the number of vertices of odd degree in a graph is always even. This proof is very easy because all you have to do is sum over all the degrees. So if you sum over all the degrees, you can see that this is twice the number of edges. Why is this? Because if you take any vertex, let's say v, right, and you are summing over all the degrees, vertices the degree of v, right? So what is the degree of v? Degree of v is precisely the number of edges incident with it. Now, given an edge, this edge is incident with two vertices. So when I sum over all the vertices degree, right, it counts. The edges are counted by both of its endpoints exactly once, right? So therefore, every edge is counted twice, and therefore the sum of the degrees is twice the number of edges. Now, this is an even number. So therefore, when you take the sum over all the degrees, if there is an odd number of odd degree vertices, that will give an odd sum, which is not possible because it is twice the number of edges. Right? So therefore, we can say that the odd degree vertices must be even in number. Now, given a graph, a sequence, okay, let's say starting from the vertex x is equal to v1, then v2, v3, etc., vk, ends in the vertex vk is equal to y, where the vertices need not be distinct. Okay, it can be distinct, but not necessarily distinct. Is called an xy walk if the consecutive pair of vertices vi and vi plus 1 forms an edge in the graph G. Okay, so this sequence is a walk if v1 v2 is an edge, v2 v3 is an edge, v3 v4 is an edge, etc. vk minus 1 vk is an edge. So this is called an xy walk because we start from the vertex v1 is equal to x and end with the vertex vk is equal to y. If those two vertices are coinciding, right, then it's a closed work because we come back to the place we started. Now, given the graph, we can look at the possible walks, right? So, for example, here I am giving the graph on 5 vertices, and 5, 4, 5, right? So 5, 4, then coming back to 5, right? So let me mark it in a different color, right? 5 to 4, right? Then I come back to 5. Then I go to 3, right? Then I go to 2. Then I go to 1. Then I go back to 2. Then go to 3, right? This is a 5-3 walk because I am allowed to repeat the vertices and edges. So therefore, this is a walk and this is a 5-3 walk. Now, this walk is not closed because it starts from 5 and ends in 3. Now, if you look at let's say 5, 4, 3, 1, 2, 3. This is not a walk. Okay, so why is that not a walk? Because if you look at the sequence, uh, 5, 4, okay, 5, 4 is fine. Then 4, 3, 4, 3 is fine. Then 3, 1. Now 3, 1 is not fine because 3, 1 is not an edge, right? So therefore, I cannot jump from 3 to 1 because there is no edge from 3 to 1. So therefore, this is not a walk. If you want a closed walk, well, you can do something like this, right? So you go start from 5. Sorry. So if you start from yes. So if you start from let's say 5, then go to 4, then go to 3, then go to 5 back, coming back, right? So this is a closed walk. Similarly, I can go from 5 to 3, then come back to 5. This is also a closed walk, right? 5, 3, 5. So this way you can think about many walks. Now, if I don't allow to repeat the edges more than once, right? No edge appears more than once in the walk, then it's called a trail. Okay. So if I look at this, for example, 4 to 5, 5 to 3, and 3 to 2, right? This is a trail because edges are not repeated. But I am allowed to repeat vertices. So I can, for example, look at 3 to 4, 4 to 5, then 5 to 3, and then 3 to 2, right? This is also a trail because I am allowed to repeat the vertices, but not edges. Now, a path is a graph of the following form. Okay, so you have a set of vertices v0, v1 to vk, and any pair of consecutive vertices in this sequence is an edge. So v0, v1, v1, v2, etc. vk minus 1, vk is an edge. So here, since this is a graph on this vertex set, you don't allow to repeat vertices or edges in this sequence. So therefore, this is basically a path. And we often write it as v0, v1, etc. vk without any space because v0, v1 is an edge, v1, v2 is an edge, etc. vk minus 1, vk is an edge. So that defines the vertex set as well as the edge set. So therefore, this is a path. Now, a walk in which no vertex is repeated is called a path in the graph. Okay. So, as a subgraph, we can see that if you look at a walk where no vertex is repeated, that is isomorphic to a path graph. So, therefore, I call it also a path, right? For example, if you look at say 1 to 2 and 2 to 3 and 3 to 5, right? So, this is a path in the graph G because no vertex is repeated, no edge is repeated, and it is isomorphic to a path graph. Right? Yeah. Now, given a path, So let us say that you are given a path. Let us say 1, 2, 3, 4, 5. Okay. What I do is that I add an edge from the endpoints, between the endpoints of this path, and then I make a new graph. Right. This is called a cycle. Okay. So given a path, let's say v0, v1, etc., vk minus 1, the graph obtained by adding the edge vk minus 1 to v0 uh, is called a cycle. Okay. So I usually denote by C, and so we have this cycle, which is an example of a graph. So this is a graph. Again, we can look at cycles as subgraphs, right? For example, here we see that 3, 4, 5 is a cycle, right? 3, 4, 5 is a subgraph, right? The graph induced by the vertices 3, 4, and 5 forms a subgraph which is isomorphic to a cycle, right? So therefore, this is a cycle in the graph G. Okay. Now, for all these, walks, trails, paths, and cycles, the length of the walk or trail, path, or cycle is the number of edges in that. Okay. So if walk, is given, then look at the number of edges, not necessarily distinct edges. All the edges are counted. Every time you go, basically you count that. So is called the length of the walk, trail, path, or cycle. So given the cycle, right? So you have the length of the cycle is 4, so there is a cycle of length 4 because there are 4 edges in this cycle. Similarly, in this path, there are 4 vertices, but there are only 3 edges. So the path of the length of the path is 3. Now, an interesting theorem is that every graph G contains a path of length small delta of G, right? The minimum degree. Okay. And the proof is a nice application. So let P be the largest path in G. Okay. So how do you show that? So we are asked to show that every graph contains a path of length small delta of G. Now we are going to show it by considering the largest path in the graph. So let P be the largest path in the graph. Let's say that it is here. Okay. So I have this path. Now maybe it starts from some vertex U and ends in some vertex V. Okay. Now what we know is that given this is the longest path, I look at the vertex U, right? Now if delta is 0, of course, we are saying that there is a path of length 0, which is a single vertex that is there. And then if you are looking at delta 1, then of course, if the graph has at least one edge only, you will have a degree, right? A non-zero degree. Therefore, if you are looking at the delta is at least 1, there is an edge. So therefore, that edge is a path of length 1. So that is okay, right? Now let us assume that delta is larger than 1, maybe. Okay. So then take this, take this graph and look at the vertex U, right? Now, if you look at the vertex U, look at the neighbors of U. What are the neighbors of U? All the vertices which are adjacent to U. Now, since the minimum degree of the graph is small delta, you must have delta neighbors, right? Now, if U has delta neighbors, that delta, if it is more than 1, then there is some other neighbor, right? So look at that neighbor. Now, can the neighbor be outside this path, UV path? I claim that it cannot be outside the path because if, this, let's say Z, the vertex Z, so UZ was, an edge and Z was not in the path UV. Then starting from Z going to U, then continuing this to V, I get another path, right? Because no vertex is repeated. And this path is longer than P that we started with. But we started with the longest path. So therefore, this is a contradiction. So therefore, what we can see is that all the neighbors of U must be in the path UV itself. Okay? So which means that all the neighbors are present in this path. Okay. Now look at these neighbors. So since the minimum degree is delta and all the neighbors of U are in this path, there are delta vertices in this path minimum, right? Other than U. So there is at least delta plus 1 vertices in this path, right? Now if there is this path with delta plus 1 vertices, we have at least delta edges there, right? So therefore that path has length at least delta. So which means that there is a path of length delta here. Okay. Now, a related theorem is that if minimum degree is at least 2, then G contains a cycle of length at least small delta of G plus 1. So here we can use exactly the same argument. We consider the longest path in the graph. Okay? So P is the longest path, U and V. And then we look at the neighbors of U as in the previous argument. All the neighbors of U are going to be present in this path. Now look at this. We already know that the path from U to the the furthest neighbor, right, has at least delta edges, right? Because there is a path of length delta in this, and that is at least delta here, right? So now it may happen that there are more vertices which are not neighbors, so which means that this path could be even longer, right? But it is at least delta. Now what we do is that we take the furthest neighbor, the delta neighbor of U in this path, and then it shows that if you take this path and this edge, right, U to this, because it is a neighbor, there is an edge. If you take this path and this edge, that forms a cycle which has strictly more than delta edges, because we have delta edges in this path and there is delta or more edges in this path, and then there is this edge. So it has strictly more than delta edges, which is at least delta plus 1. So there is a cycle of length larger than or equal to delta plus 1. So these two are very nice proofs of this fact using what is called extremality. Okay, we will come to this kind of extremality arguments in the future. So we have these two theorems. Now we look at the adjacency matrix of a graph G. Okay, so given a graph G, we can define in a matrix related to this, which is called the adjacency matrix, which basically represents the information about the graph. So what you do is the following. So you look at this n vertex graph, let's say v1 to vn. Then I define the adjacency matrix of the graph as follows. So given A is equal to Aij, which is an n cross n matrix, Aij is defined to be 1 if Vi, Vj is an edge of the graph and 0 otherwise. So given this matrix, you can immediately see which pair of vertices are adjacent, and therefore that gives you the entire graph, right? Now here is an example of a graph and its adjacency matrix. Okay, so you have this graph on 4 vertices, 1, 2, 3, and 4. And what is the adjacency matrix? You write 1, 2, 3, 4 here, corresponding to 1, 2, 3, 4 here, and whenever so 1 is adjacent to 2, so therefore 1 to 2 there is this entry 1. Then 1 is not adjacent to any of the other things, so therefore all these values are 0, right? And then you have 2 is adjacent to 1 to 2, so there is, because it's going to be the matrix is going to be symmetric, because you can see that whenever 1 2 is is an entry, 2 1 is also an entry, because 1 and 2 are adjacent. because so we will get a symmetric, right? Symmetric matrix. So similarly, 3, 2 and 4, 2 are edges. So similarly, you have 2, 3 and 2, 4 as 1. And of course, the diagonal entries are 0, right? Because there is no edge from a vertex to itself in our graphs that we are looking at. Of course, there are graphs where these kind of edges are allowed, which are called loops, okay, like this. But we will not look at those graphs at the moment. And when we are using them, we will specifically mention that. Okay, so they are not simple graphs; they are graphs with the loops, and you are also allowed to have more than one edge between two vertices, which is called parallel edges or multiple edges. So these things we will come in the future maybe, but at the moment we can assume that these are not present. We have the following theorem. Given a graph G and its adjacency matrix, let's say A, then the ijth entry of the kth power of the adjacency matrix gives the number of walks of length k from the vertex vi to the vertex vj in the graph. So if you take the adjacency matrix and take the kth power, then the ijth entry gives you the number of walks of length k from vi to vj. So we can easily prove this using the matrix product. So here is the proof. So let us first look at the base case when base case k is equal to 1, right? So when k is equal to 1, we have the a raised to k is basically the adjacency matrix. Now what is a of ij? A of ij is the ijth entry, and this is precisely 1 when there is an edge from vi to vj, right? So when there is an edge from vi to vj, there is a walk of length exactly 1 from vi to vj, right? And that shows that there is precisely a walk of length 1, right? One walk of length 1. And when there is no edge, there is the entry is 0, and there is no walk of length 1 if there is no direct edge between them, right? So you have to go to at least 2 edges to do that. So therefore, uh, the base case is fine, right? Okay. So now let us use the induction hypothesis and say that, okay, the result holds for any value of k less than n. Okay. So hypothesis the claim holds for k less than n. Okay. So now what we have is that, so if you take let's say the a raised to n of ij, right? We want to show that a raised to n of ij is precisely the number of walks of length n from I to j, right? Once you do this, we have the result by induction. Now what is this? By definition of the matrix product, what is this? This is equal to a into a raised to n minus 1 of ij, right? So this is the product. Then you look at the ijth entry, right? Now what is the ijth entry of this product? Again, if you remember matrix multiplication, right? So this is summation overall, let's say m ranging from 1 to the order of the matrix, which is the order of the graph G, right? Then a of I comma m, right, multiplied with a raised to n minus 1 of m comma j, right? Now, what is a raised to n minus of m comma j by induction hypothesis? This is the number of paths of length n minus 1 from Vm to Vj. Now, if there is an edge from Vi to Vm, then now I can make an edge. I can make a walk from Vi to Vm, then Vm to Vj. I have a walk of length n minus 1. So therefore, together I get a walk of length n, right? So if Im is an edge, then I get all these paths will be counted towards the number of paths. Now this is for any vertex m. So now I can do for every such vertices, right? So look at all the vertices. I go from I to that vertex. If there is an edge from I to that vertex, that entry will be exactly 1. And then you look at the paths of length n minus 1 from that vertex Vm to Vj, and that if that whatever that number is, that will be counted towards the total sum. So this will tell you that will give you the number of walks of length n from Vi to Vj, right? Because every such path basically goes from Vi to some vertex, right? One of these 1 to cardinality of G, that many, or one of these vertices in the graph, and then continue from there to J with these many steps. So therefore, there is a one-to-one correspondence, and then we see that this is precisely what we wanted. So this proves the result. The claim holds, right? Okay. Now we define another related notion. So this is called directed graph. So a directed graph is basically a pair V comma A, where V is a set of vertices as in the case of our graphs, and A is a set of ordered pairs of vertices called arcs. Okay, so the difference is that here instead of two element subsets, we are looking at ordered pairs of vertices. Okay, so these are called arcs because this ordered pair tells you that U to V there must be an edge or an arc, but it does not always mean that there is an arc from V to U, right? So I can, so for example, if you are talking about like one way traffic, right? I can go from A to B, but B to A I cannot come directly. Maybe I have to go somewhere else, right? But of course, that is also possible. You can have for example, in this you see that I can go from this vertex to this vertex, and I go from here to backwards. So that is also allowed, but one edge or one arc says that I can go from, so that every arc has a starting point and an ending point, right? Initial point and end point. So this is a directed graph. You can think of the directed graph as representing relations between objects which has some kind of direction to it. For example, if you are talking about people, and then like I say that A is the father of G, right? I mean A is the father of B. Then basically this is a one way relation, right? Because A, when you talk about the parent relation, right? This is one way relation. So similarly, there are other things like as we said, traffic, one way traffic. These kind of things can be represented by directed graphs, right? So here is an example of a directed graph. You have these vertices. Let's give some names: 1, 2, 3, 4, and 5. So in this, you can see that 1, 3 is an arc, right? So you have the vertex set B is equal to set 1, 2, 3, 5, and then you have the arc set, which is the ordered pair 1, 3, then 3, 4, Then you have 2 to 1, right? Then you have 2 to 4. Then you have 4 to 5 and 5 to 4, right? So these are ordered pairs, and this defines the directed graph. Okay. Now, if you look at the set of all vertices, let's say y, such that xy is an arc in the graph. So this set, look at the cardinality. This is called the out degree of x. So which means that you are talking about the edges that are going from x to some other vertex, right? So in this case, for example, I'm looking at this vertex 2, and then there are these two edges, 2 to 4 and 2 to 1, right? These two edges are going out of the vertex 2. So therefore, the out degree here is the cardinality of these two edges, which is 2, right? On the other hand, if you take the vertex 3, if you take the vertex 3, right? 3 has 3, 4 is going out, but 1, 3 is not going out of it. Therefore, I only count this for the out degree. So the out degree of 3 is 1. Similarly, what is the in degree? The in degree of a vertex is the cardinality of the set of all y such that yx is an arc of the graph G, right? So I am, from all the vertices from which there is, right, there is an edge, there is an arc to x. So the in degree of 3 is 1, as we just notice here. In degree of 2 is 0, right? There is no vertex and no edge or arc coming to 2. And if you look at the vertex 4, it has in degree 3 because 2 to 4, 3 to 4, and 5 are coming in. And out degree 1 because 4, 5 is the only are going out.